Welcome to the video lecture by Dr. Viju Vastuvan for the course Calculus 2 Math 112. This is an explanatory video for the PowerPoints available on Blackboard for week number 9. He will solve some problems from the chapter 7.8 Improper Integrals. Up to now, we have focused on definite integrals with the continuous integrands and finite intervals of integration. In this section, we will extend the concept of definite integral to include infinite intervals of integration and integrands that become infinite within the interval of integration. We have seen in previous theorem that continuous functions are integrable and are unbounded functions with finitely many points of discontinuity also are integrable. We also observed that the functions that are not bounded on the interval of integration are not integrable. For example, if you have a vertical asymptote within the interval of integration, the function will not be integrable. Our main objective in this section is to extend the concept of definite integral to allow for infinite intervals of integration and integrands with vertical asymptotes within the interval of integration. We will call the vertical asymptotes as infinite discontinuities, and we call this integrals with the infinite intervals of integration or infinite discontinuities within the interval of integration as improper integrals. You understand something? So the point is, again, now we are going to discuss an improper integral. We are going to get integrals of this type. Either you have both the limits are infinite limits or any one of them, a constant limit and upper limit is infinity, or upper limit is constant and lower limit is an infinity. Or you can get a function which is to be integrated as x minus this function, 1 f of x is equal to 1 over x minus 1. It's not defined for x is 1. It has vertical asymptote at x equal to 1, isn't it, this function? So when you integrate this function from 0 to 2, you should be careful. This function is not continuous at x equal to 1. So we are calling these kind of integrals, either they have infinite intervals, or within the interval of integration there is vertical asymptote. So we are going to solve these kind of problems in this case. Let's see some more cases, the improper integrals with the infinite intervals of integration. See, in the first three cases, here in the first case upper limit is positive infinitive. Second case, the integrand is okay, it's not defined at x equal to 0, but x equal to 0 is not in the limit. Here e raised to x, the lower limit is negative infinity, and in third case both the limits are infinity, isn't it? And the second case of improper integrals, here negative 3 to 3 you are integrating, but between negative 3 and 3 there is a point 0. So this function 1 over x square is not defined for x square, x equal to 0, because at x equal to 0 we have a vertical asymptote. So this is an improper integral. Of course, the same for this case. At the lower limit you will find x equal to 1, you will find vertical asymptote. And the upper here, tan will have vertical asymptote at x is equal to pi over 2, which is lying between 0 and pi. So these three are other different cases of improper integrals. So you can check and identify what are these three cases, why these three are improper integrals. Now, so some graphs have been given of the function is y is equal to 1 over x square, isn't it? So you are integrating from 1 to infinity. When you integrate 1 to infinity, what we are actually doing is we integrate from 1 to b. You get a result here. When you integrate the function from 1 to b, you get a finite answer here, 1 minus 1 over b. Now we take the limit of this answer to be, for this limit 1 minus 1 over b is our answer for the integration for the definite integral. And now we take a limit b approaches positive infinity. If you get a finite answer, the integration converges otherwise it diverges. That's what we are going to say. So when v is infinity, this will be 1, obviously. So this is what we are going to do here. Some different cases are given in this. See, so when the b is 2, the area is half. B is 3, the area is 2 over 3. When b is 4, when you are increasing this side, the area is increasing towards 1. So when you approaches x, when your x approaches infinity, your area approaches 1. That's what we are getting from these graphs. The theorem, we are coming to the theorem or definitions to solve the problems of this chapter. The improper integral of a function f over the integral interval from a to positive infinity. That's what given, a to positive infinity. The upper limit is infinity, isn't it? So how to integrate this one? So upper limit will be replaced by a constant b, and then we take the limit b goes to positive infinity. So here a curve may be like this, infinitely going on. See, we are starting from here a, and this upper limit has not been given, it's going infinity. So we stop at some b. We find the integration for the function f of x from a to b, and we take the limit b goes to positive infinity. So obviously you can guess, if the lower limit is negative infinity and the upper limit b, f of x dx, can you write your own definition? So it will be limit, you can take the lower limit as a to b, f of x dx, and let a approaches negative infinity. So the graph may be like this. So if you are integrating from this is from negative infinity towards b, this is going somewhere to negative infinity. You take some a here, from a to b we integrate, and then we take a approaches negative infinity. That's coming the definition 7.8.3. right? Now let's be back to the theorem 7.8.2. what it suggests is, when the constant is 1, when you integrate from 1 to positive infinity, a function in the form 1 over x to the power p dx. So it can be 1 over x square, 1 over x cube, 1 over root x, anything. The power p, in the case of root x, the power p is half. So if the power p is greater than 1, strictly greater than 1, then the integration converges to 1 over p minus 1. If the p value, the power of x, is less than or equal to 1, then the integrand is converged. So you don't need to apply the limit or constant. Directly from the power of p you can identify. So this theorem is very important to solve the coming problems. Let's move ahead. So this has been 7.8.3 has been seen. Improper integral with a lower limit as infinity. We have seen it. The improper interval of f over the interval, both the limits are infinities, negative and positive infinity, isn't it? So this is negative infinity to positive infinity. So first we will write it negative infinity to some point c, and from c to, so this one will be dealt with the first part. We separate this integrand negative infinity to positive infinity, the real line from negative infinity to positive infinity, into two parts. There is a c between them. So in the first part, first integration takes place. In the second part, c to positive infinity, second integration takes place. The first part can be done by using definition 7.8.1, and the second part of this integration can be done by using 7.8.3. The improper integral said to converge if both the terms converge. If one of them diverges, the entire integration diverges. Some figures have been given here. If the upper limit is a vertical asymptote, if this is, see in this graph, you are supposed to integrate from a to b, but at the point b the function has not been defined. It's a vertical asymptote, isn't it? So in this case also we use the same technique. Here we take a value k and we integrate from a to k, the same function f of x dx, and we assume k approaches b. See, it's not approaching now infinity, k approaching b from the left side. So left limit k approaches b from the left side. This is the case formula for this one. Now it's not infinity. Now the limits are not infinity, but one of the limits is a vertical asymptote, or sometimes we get there is a vertical asymptote between these 2 points a and b. So in this case this is not approaching infinity, but we will either find left limit or right limit cases. So that's what here, that's explained here. K approaches b. This is what we have seen in the previous slide here. K approaches b from left side from a to k f of x dx. And if f is continuous on the interval, so here we go. So the it's given f is continuous on the interval a to b except for an infinite discontinuity at a. So at the lower limit a, we find a vertical asymptote. Isn't I mean infinite discontinuity. Then this a will be replaced by a k and k. So you have a and b, isn't it? The function may not be touching a, so it may be like this. You want to integrate here, but at a you have a vertical asymptote, isn't it? So what do you do? Before a you can take a k, and k approaches a from the positive direction. That is, k approaches a from the positive direction. So you get a right limit of k at a. So when the second case, when the discontinuity of the point c inside the b, somewhere inside the b, between, this is the interval a and this is the upper limit of b. So there is some point c at which the function has a vertical asymptote. You will find a to k, you can separate into two parts, a to c and c to b. Both should be dealt in different cases. So first a to c will be dealt to by using this theorem 7.8.4, and c to b can be dealt with the definition 7.8.5. That's it. We are going to use these theorems again. Now this is the case where vertical asymptote, there is a discontinuity c at c. The function has not been defined at c in between a and b, but you have to integrate from a to b where the function has a discontinuity at c. Fine. Let's go to the. So some warning has been given here. Sometimes it's looking very easy to integrate from 0 to 2. You will think that this function is this is just a definite integral. You can go ahead to integrate by use substitution, but carefully listen. Between 0 and 2, x is equal to 1 will make this function in the denominator it is 0, so you will get infinity. The function has not been defined for x equal to 1, so x equal to 1 lies between 0 and 2. Should be careful in these cases. This is a case of improper integral. So let's go to the, so how to integrate this one has been explained here. You can go through from the textbook. Let's go to exercise problems. Exercise set 7.8. Let's solve problem 3 at first. There are many problems, only 4 and 7 problems we have to deal with. Let's solve one by one. Let's start with the problem number 3. Okay, what's going on here? Is an integration. Is it a proper integral, or is it improper integral, or what? How do you identify? The upper limit is, see, we are solving problem number C. The upper limit has been given as infinity. So we are to replace the upper limit by a number 0 to b. We will write it b, isn't it? And write the function e raised to negative 2x dx. And we know the b limit b should approach positive infinity. That's it. So integrate as usual by using fundamental theorem of calculus part 1. What is integration of exponential negative 2x? Is e raised to minus 2x over minus 2 from 0 to b, and a limit b approaches positive infinity is the additional information. Now what happens here? Negative 1 over 2 can be written outside, and upper limit x will be replaced by b e raised to minus 2b minus e raised to 0 is 1. And now limit b approaches positive infinity. What happens here? When b goes to infinity, e raised to negative infinity, you should remember the rule, e raised to negative infinity is 0. The first term will be 0. So minus 1 by 2, 0 minus 1. The answer is positive 1 by 2. So the integration converges. You got a finite answer. Now let's go for the next problem. Problem number 4. Here again the upper limit is positive infinity, so it's an improper integral negative 1. So we have to rewrite this one as upper limit is b x over 1 plus x square dx, and then take a limit for b approaches positive infinity. And remember, if it is lower limit, then this approaches negative infinity. Probably problem number 10 is coming up. So integrate this one. We know this is the integration we have seen many times. The derivative of the denominator is numerator. You should have a 2 here, isn't it? 2 is missing. So this is ln. This is ln. You can use substitution method or any method. You can find the answer of this integration as ln of 1 plus x square, and there is a 2 missing, so 1 over 2. And now take limit b goes to positive infinity. The limits of this integration, negative 1 to b. So in the next step we will write limit b approaches positive infinity 1 over 2 1 over 2. Substitute the upper and lower limit. What do you get? Upper limit is b ln 1 plus b square minus, when lower limit is substituted, minus 1 square is positive 1, ln 1 plus 1 ln 2, isn't it? So okay, what happens here? Limit b approaches positive infinity 1 over 2. I just repeat the step again. Why? So substitute b is infinity, ln infinity is infinity, so everything will be infinity. There is infinity, positive infinity. So this diverges, this integration diverges, does not have a finite answer. Now let's go ahead to find the solution for problem number 10. Problem number 10. Okay, what's the case? You should have an idea of the integration of 1 over x square plus integration of 1 over x square plus a square, which is 1 over a tan inverse x over a. This should have been there in your mind. Okay. Okay, fine. Let's use it here. The lower limit, you remember the lower limit is negative infinity, so it should be replaced by another constant. We call it a. Lower limit a to upper limit 3, and 1 over x square plus 3 square dx, and limit, the lower limit a should approach negative infinity, isn't it? Okay, so what is happening here? Integration of this one by this rule, the given formula 1, what do you get? 1 over 3 tan inverse x over 3 from a to 3, and now the limit remains a approaches negative infinity. So what happens here? This step, limit a approaches negative infinity, 1 over 3 tan inverse 3 over 3 is 1, tan inverse 1 minus tan inverse a over 3. What is happening? So now just substitute a is negative infinity, so this will be 1 over first term is 1 over tan inverse 1 is pi by 4, second minus tan inverse negative infinity will be pi by negative pi by 2. So tan inverse a will be replaced by negative infinity, so tan inverse negative infinity will be negative pi by 2. This is pi by 4 plus pi by 2. You get 1 over 3 outside, inside 3 pi over 4. So the answer is 5 over 4. That's the end of this problem number 10. Let's go ahead to find 16. So problem number 16. We are going to start problem number 16. Okay. Substitution method. So in here both the limits are infinite. Lower limit is negative infinity, upper limit is positive, so we can replace both of them just like by taking a point between negative infinity and positive infinity. Will take a point of 0, so we will separate this one from negative infinity to 0 e power negative t divided by 1 plus e raised to negative t dt. Next is from 0 to positive infinity, e raised to negative t dt over 1 plus e power minus 2. We will replace the infinity limits by constant and apply the limits. Before that we use substitution method. Let u is equal to e raised to minus t. So what happens to the denominator? It will be u square 1 plus u square. What is du? When you find e raised to minus t divided by minus 1 into dt. So dt becomes negative, e raised to minus t dt becomes negative du. In this integration we are going to replace this one, and of course we will be back to u e power t and then substitute the limits. So what happens here in the next sense, the lower limit is infinity, so we will take a limit from a to 0, and this will be negative du divided by 1 plus u square. Here a approaches negative infinity. Second part, limit b approaches positive infinity from 0 to b. This is again negative du over 1 plus u square, and we should remember the formula that we have used in the previous problem, tan inverse for 1 over x square, isn't it? So the next step, I'm going to step by solve it. The next step will be What is the next step possible for this one? Negatives commonly has been taken by, and then there is a limit a approaches negative infinity. The first part is tan inverse u from a to 0. Second part is limit b approaches positive infinity, tan inverse u, and the limit is 0 to b. That's all. When you simplify this one, you get the answer. And the negatives outside, and what is tan inverse 0 is, no, the u should be replaced. What is your choice of u? U is e raised to negative t. So next time, limit a approaches negative infinity, and this is tan inverse e raised to negative t, and from it is a to 0 plus limit b approaches positive infinity and tan inverse e raised to negative t, and the limit is from 0 to b. This is a common bracket, negative is outside, right? Now in the next step, we will substitute the upper and lower limit, and then in the first case we take a goes to negative infinity, and second case b goes to positive infinity. Let's check what is happening here. Next step, substitute upper and lower limits. Tan inverse e power minus infinity. See, so what is happening here? Tan inverse 0, e power 0, e power 0 is 1, tan inverse 1. So I write here, there is a limit a approaches negative infinity. So here tan inverse 1 minus tan inverse e raised to minus the limit e raised to minus a plus this is also here limit b approaches positive infinity, tan inverse e raised to minus b minus e raised to 0 is 1, tan inverse 1. So what do you get? In the first term, tan inverse 1 is pi by 4, last term tan inverse 1 pi by 4, and it a should goes to negative infinity, so tan inverse of negative infinity of infinity. This is the next term, isn't it? So I write it here, I write it at the top, and when you apply tan a goes to negative infinity, this will be e raised to negative a will be e raised to positive infinity, which is infinity. So tan inverse infinity is pi by 2. So first one is pi by 4 minus pi by 2, because there is a negative outside. There is a negative outside, right? Plus here when b goes to infinity, this will be e raised to negative infinity to 0, 0 minus pi by 4, pi by 4. So what do you get? Pi by 4, positive pi by 4, negative pi by 4 will be cancelled. It will be negative pi by 2 with the negative outside. The answer is pi by 2. The answer for this problem number 16 is pi by 2. And the next three problems, the last three problems of this chapter. Problem number 17. What's happening here? Is it improper integral? You are supposed to integrate from 0 to 4. So at x is equal to 4, the function has a discontinuity. So we cannot directly integrate from 0 to 4. This is improper integral and should be addressed carefully. We should So we should remember that before so we are getting from 0 to 4. At this 4 the function has discontinuity. So before 4 we have to take a constant k. So integrate from 0 to k and then take limit from k to 4. The left limit of this one. K approaches 4 from the left side. So left limit of k at 4, right? So that's what we have to do it here. Limit k approaches 4 from left side and 0 to k 1 over x minus 4 whole square dx. Now again substitution method should be used. U, what is your choice? U is x minus 4, therefore du is dx. So this integration becomes limit k approaches 4 from the left side. So integral 0 to k u to the power negative. This is u square in the denominator. So in the power numerator it will be u square, u over negative 2, and du will be dx will be du. So that is it. Just integrate it. Limit k approaches 4 from the left side direction. Integration of this one is u raised to negative 1 over negative 1 from 0 to k, and limit k approaches 4 from the left direction. You will get it. The negative is outside. So 1 over u. 1 over u minus 0, isn't it? So 1 over u is. So finally you will reach a limit k goes to 4 from negative direction. 1 over u is 1 over u, and when x is 0, actually when x is u is 0, actually it is 1 over u from 0 to k, isn't it? 1 over u from 0 to k negative. So 1 over u should be replaced here. It will be negative 1 over x minus 4, isn't it? When you substitute upper and lower limit, now I will solve it the next slide. When you substitute upper and lower limit, there is negative. You will get negative limit k approaches 4 from left side. Upper limit is k. X should be replaced by k. So 1 over x minus 4 will be k minus 4, and minus 1 over x minus 4 will be 0 minus 4 will be 0 minus 4. This is what we get. Now substitute x goes to 4. So from the left limit, so roughly you can try this one. Limit k approaches 4. From left direction, 1 over k minus 4 by using the tables or the concept we have studied in the beginning of this paper. It will approach negative infinity. So negative infinity, there is a negative outside, so totally it will be positive infinity, isn't it? And therefore it is this integration diverges. And let's start problem number 23. I will solve one of these two problems, 23 and 28, and we can practice similar problems with test 2. That will be the end of this chapter. Let me go ahead with the 23. 23. What's going on here? Why this is improper integral? See, and there is no infinity on the limits. And the next question is whether at the lower limit and the upper limit whether the function is continuous or not, or is there any point between pi by 3 and pi by 2 the function is discontinuous. Will we check? When you substitute pi by 3 here, cosine pi by 3 is 1 by 2. So 1 by 2 into 2 will be 1, so 1 minus, so it's 0, the denominator will be, the function will be infinity, isn't it? So that's why, so the lower limit has a problem. We replace upper limit, has no question, no problem. Between pi by 3 and pi by 2, this function will not have any trouble. So problem occurs only at the lower limit. We can remove the lower limit, place a constant k there. So you are from a to b, the problem at the lower limit. So you take a k here, isn't it? And you integrate from k to b, and then finally your k approaches a from the positive direction. That's what your a is pi by 3 here. So we are writing limit k approaches pi by 3 from the positive direction, integral k to pi by 2. Now this integrand term should be replaced by some substitution. U let u is equal to 1 minus 2 cosine x. So what happens for du? Du is 0 minus 2 cosine, when you differentiate cosine, minus sin x dx. So du is du over 2 sin x dx. So when we substitute, so when we sin x dx will be du over 2, so this will be 1 over u and du over 2. So integrate 1 over u to the power half, so this under square root. So you will get here limit k approaches pi by 3 from the positive direction. This integration is 1 over 2 from k to pi by 2 u to the power negative half and du. Answer is the limit k approaches pi by 3 from positive direction. The 1 by 2 you can keep outside, the 1 by 2 is outside. Okay, the integration of this u power negative half is u power half over half, and the limits of u will be from k to pi by 2, and we have to replace the value of k, I mean u is 1 minus cosine 2x. So in the next step we will write limit k approaches pi by 3 from positive direction 1 by 2, and this 1 by 2, this 2 1 by 2 can be cancelled, you will get half u, only u, that is 1 minus cosine x to the power half, and the limit is from k to pi by 2. So the next step we will solve it. It is equal to limit k goes to pi by 2 from the positive direction. When you substitute upper limit as pi by 2, it will be 1 minus 2 cosine pi by 2, and when you substitute lower limit as k, it is 1 minus 2 cosine k. Here there is a power 1 by 2. Now what happens? Limit k approaches pi by 3 from the positive direction. Cosine pi by 2 is 0, so this is 1 to the power half is 1 minus cosine k. This is 1 minus 2 cosine k to the power half. Now k is pi by 3. Substitute the limit. When you take the limit, the first time is 1 minus, this will be pi by 3, 1 by 2 is 0. Pi by 3, cosine pi by 3 is half. Cosine pi by 3 is half, so half into 2 will be 1, 1 minus 1 is 0, so this is 0, so the answer is 1. So the integrand, the problem number 23 gives the answer as 1. That's all. Try all other problems from this chapter. Thank you very much. You can send your doubts through comment section, or you can ask doubts through email ID, WhatsApp, or of course through Blackboard. And so try to solve the assignment problems in time. Thank you very much, students.